The universe has a way of delivering surprises just when we think we've figured out the rules. On November the 9th, 2025, astronomers Frank Nebling and Michael Boehner captured something that has left the scientific community scrambling to rewrite textbooks. Using twin telescopes during a precise 15-minute observation window, they photographed the interstellar visitor known as 3I Atlas. What emerged from their data wasn't just unusual. It was impossible according to everything we understand about how comets behave. The image reveals massive jet structures erupting from this mysterious traveller. Not the typical single tail we expect from comets, but three distinct outflows shooting into space with breathtaking intensity. Two anti-tail jets pierce directly toward the Sun, stretching nearly 1 million kilometres into the void. That's roughly 3 times the diameter of the Moon as seen from Earth. But the third structure defies every model we've built. A columnated beam launches away from the Sun, extending an incredible 2.85 million kilometres. To grasp that scale, imagine a structure 7 times the distance from Earth to the Moon. These aren't gentle wisps of dust and gas. These are colossal formations that dwarf anything astronomers have witnessed from natural comets. The scale alone represents a 1,000-fold increase over the glowing halo Hubble photographed around 3I Atlas back in July. We're witnessing structures that challenge the fundamental physics of how interstellar objects should behave. And here's where it gets truly perplexing. These jets are operating under conditions that shouldn't allow them to exist. When typical comets approach the Sun, ice sublimates from their surfaces at relatively modest speeds of about 0.4 kilometers per second. That's roughly the speed of sound in gas at this solar distance. It's a gradual process powered purely by sunlight heating frozen materials. Yet for these massive jets to extend as far as they do, they would require continuous material ejection for months. The tail jet alone would demand at least 3 months of constant outflow. The anti-tail structures would need minimum 1 month of sustained activity. That represents an enormous amount of persistent behaviour from what should be a relatively small interstellar fragment. But the physics become even more troubling when you consider the environment these jets must operate within. Harvard professor Avi Loeb calculated something remarkable about these anti-tail formations. For them to extend nearly 1 million kilometres against the solar wind, they must possess incredible density and pressure. The solar wind typically races at 400 kilometres per second, 1,000 times faster than normal comet outflow. Yet somehow these jets are pushing against that cosmic hurricane and winning. The mathematics reveal something shocking. The mass loss rate required to maintain these structures approaches 50 billion tonnes per month. Let that number settle in your mind. 50 billion tonnes every single month. That's comparable to the minimum estimated mass of the entire object itself. We're looking at a body that would need to be ejecting its own weight in material every few weeks just to sustain what we're observing. Before we dive deeper into this mystery, make sure you hit that subscribe button. What we're about to explore over the next several weeks could fundamentally change how we understand visitors from beyond our solar system. The data streaming in from observatories worldwide is unlike anything we've encountered before, and you won't want to miss a single revelation. So we have an object losing mass at rates that seem almost impossible for natural processes. We have jet structures on scales never before witnessed in our solar system. We have formations that, based on these mass loss calculations, would require the parent body to be at least 10 kilometers in diameter just to survive this kind of activity, without complete disintegration. Here's where the timeline becomes crucial to understanding this puzzle. For months leading up to its closest solar approach on October 30th, 3I Atlas showed virtually no signs of the dramatic activity we're witnessing now. Astronomers had been tracking it steadily since July, and it appeared relatively quiet. No significant acceleration beyond gravitational forces, no massive outbursts lighting up the sky, nothing to suggest it was preparing for this kind of spectacular performance. Then something changed. As it swung around the Sun at perihelion, reaching its point of maximum solar heating, everything transformed. Multiple jet systems activated seemingly overnight. The behaviour shifted so dramatically that it's as if an entirely different object emerged from the solar encounter. Some invisible switch had been thrown, awakening processes that had remained dormant throughout its long journey through interstellar space. Traditional comet science offers one potential explanation. Perhaps pockets of volatile ices, buried deep beneath protective surface layers for potentially billions of years, suddenly became exposed to intense solar radiation during perihelion. The thermal shock could trigger massive outbursts as these ancient materials rapidly sublimate under the sun's assault. We've observed similar outburst events in other comets, though never on this scale or with this degree of organization. But other voices in the scientific community, including Professor Loeb, are raising different questions entirely. What if these aren't jets caused by simple ice sublimation? What if we're observing something that operates according to different principles altogether? Consider the implications if these formations resulted from some form of propulsion system rather than passive outgassing. Chemical rockets, the kind we use for space exploration here on Earth, generate exhaust velocities of 3 to 5 kilometers per second. That's 10 times faster than natural comet sublimation. Ion thrusters, representing more advanced propulsion technology, achieve speeds of 10 to 50 kilometers per second. With those kinds of exhaust velocities, the required mass expenditure drops dramatically. Instead of needing to eject the object's entire mass every month, the fuel requirements could shrink by 1 to 2 orders of magnitude. Perhaps less than 1% of the total mass would suffice to create the structures we're observing. Suddenly, the impossible mathematics become merely challenging. Now, I want to be absolutely clear about something. I'm not claiming that 3i Atlas represents artificial technology, but I am pointing out that the observational data is forcing us to ask questions we never anticipated having to consider about an interstellar visitor. The numbers simply don't align cleanly with conventional comet behavior. When mathematical models fail to match reality, scientists have a responsibility to explore alternative hypotheses, regardless of how unconventional they might initially appear. This marks the third confirmed interstellar object we've detected passing through our solar system. The first was Oumuamua in 2017, which displayed its own collection of puzzling characteristics that challenged standard interpretations. The second was Comet 2I Borisov in 2019, which behaved much more like astronomers expected from a typical comet. Now we have 3i Atlas, which seems to occupy a category entirely its own. What makes this moment particularly exciting is that we're witnessing these events unfold in real time. Telescopes across the globe are now tracking 3i Atlas as it continues its outbound journey from the Sun. Its angular separation from our star recently crossed 30 degrees, meaning Earth-based observatories can finally observe it again without solar glare overwhelming their sensitive instruments. Over the coming weeks, astronomers will be conducting detailed measurements of these jet compositions, their velocities, their density distributions, and searching for any fragments that might have separated from the main body during the intense perihelion passage. These observations will help determine whether we're witnessing an extraordinary natural phenomenon operating at the extreme end of known comet behavior, or something that challenges our fundamental assumptions about what's possible in the universe. The November 9th images represent just the opening chapter of this investigation. They're a preview of the discoveries yet to come. We're living through a remarkable period in human history. For the first time, we possess the technological capability to study objects from other star systems in unprecedented detail. We can analyze their chemical compositions, track their precise trajectories, and search for clues about the environments they originated from billions of years ago. Every piece of data we gather brings us one step closer to understanding our place within the broader galactic community. 3i Atlas currently sits about 326 million kilometers from Earth. That might seem impossibly distant by terrestrial standards, but in astronomical terms it's practically next door, and it's getting closer to us. On December 19th, it will reach its nearest approach to Earth at a distance of 269 million kilometers. That's still safely distant, about 100 times larger than the extent of its massive jet structures, so we face no danger from this encounter. But it will provide our best opportunity yet to study this enigmatic visitor with maximum resolution and sensitivity. The question that haunts every observation session is simple, yet profound. What exactly are we looking at? Is 3i Atlas a massive interstellar comet experiencing an unprecedented outburst of activity? Could it be a fragment of a shattered world, tumbling through space and violently outgassing as it encounters our sun's radiation for the first time in eons? Or might it represent something else entirely, something that doesn't fit neatly into our existing categories of natural solar system objects? The honest answer is that we don't know yet, but that uncertainty is precisely what makes this investigation so compelling. We're conducting science in real time, following the evidence wherever it leads us, without preconceived notions about what we should or shouldn't find. Right now, that evidence is pointing toward questions we never imagined we'd need to ask about visitors from the stars. The next few weeks will be absolutely critical for unraveling this mystery. Make sure you're subscribed and have notifications enabled, because the data coming in could reshape our understanding of what travels between the stars. Whether 3i Atlas proves to be a natural phenomenon operating at extreme scales, or something that challenges our assumptions about the universe, we're witnessing history in the making. The universe has always been full of mysteries waiting to be uncovered. 3i Atlas might represent just the beginning of discoveries that will transform how we see our place in the cosmic order. The story is far from over, and the most revealing chapters may still lie ahead. But let's step back and examine what happened during those pivotal hours when 3i Atlas made its closest approach to the Sun. Because this is where the narrative transforms from puzzling to genuinely extraordinary. October 29th and 30th, 2025. These dates are now permanently etched in the minds of astronomers studying this object. 3i Atlas reached perihelion, swooping to within 203 million kilometers of our star. For context, that places it just inside the orbit of Mars. For an interstellar wanderer, this represented its moment of maximum solar bombardment, maximum thermal stress, and apparently maximum awakening. What transpired next has ignited fierce debate throughout the global astronomical community. In the days immediately following perihelion, observers began documenting something completely unexpected. Not merely the 3 colossal jets we've already discussed, but a total of 7 distinct jet structures radiating from 3i Atlas. 7 separate streams of material, each oriented in different directions, creating what can only be described as a complex fireworks display frozen in the vacuum of space. Multiple jets aren't entirely unprecedented in comet science. We've witnessed comets with several active regions across their surfaces, each producing its own outflow as different areas become exposed to direct sunlight. But the geometric arrangement, the synchronized intensity, and the precise timing of these 7 jets are raising serious questions among researchers who've spent decades studying these objects. Professor Avi Loeb has been following this development closely, and he's asking a question that makes some traditional comet scientists deeply uncomfortable. Did 3i Atlas experience partial fragmentation near the Sun? Here's why this possibility matters so much. When comets break apart, we typically observe distinct fragments, each following its own slightly different trajectory. We see debris fields spreading across space. We witness dramatic brightness changes as fragmentation exposes fresh ice surfaces to solar radiation. It's usually a violent, observable spectacle. But here's the puzzle that's keeping astronomers awake at night. While we're documenting these 7 jet structures and the massive streams of material being ejected, we're not seeing clear evidence of multiple fragments moving along separate orbital paths. The observations reveal jet structures and material outflows, but the central object appears to remain largely intact, or at least mostly coherent. This creates a fascinating scientific dilemma. Either 3i Atlas underwent partial fragmentation where pieces separated, but the main body survived the encounter, or something else entirely is driving these multiple jets to appear simultaneously with such remarkable coordination. Let's examine the fragmentation hypothesis first. Comets are notoriously fragile structures. They're often compared to dirty snowballs, loose aggregations of ice, dust, and rocky material held together by their own weak gravitational attraction. When a comet ventures too close to a star, thermal stress can literally tear it apart. We've witnessed this destructive process before with other comets. The most famous case remains Comet Shoemaker-Levy 9, which shattered into multiple pieces before colliding with Jupiter in 1994. We've also observed comets fragmenting as they round the Sun, creating spectacular but brief displays before vanishing completely into dispersed debris. If 3i Atlas experienced even partial fragmentation, it would explain the sudden appearance of multiple jet systems. Each fragment or each newly exposed surface region could generate its own outgassing stream. The intense solar heating at perihelion would trigger rapid sublimation of materials that had been buried and protected for potentially billions of years during its journey through interstellar space. But there's a significant problem with this straightforward explanation. The energy output and sustained duration of these jets seem inconsistent with simple fragmentation events. Remember, Maintaining these structures requires massive, continuous outflow over weeks or months. Fragmentation events typically produce much more explosive and short-lived displays. This brings us to alternative explanations that venture into less conventional territory. What if these 7 jets aren't the result of passive sublimation or fragmentation at all? What if they represent active processes operating according to principles we haven't fully considered? Before dismissing this as scientific speculation, consider that we're already comfortable with the concept of active geology on other worlds. We understand that moons like Enceladus and Europa possess geysers powered by internal heat sources. We know that geological activity can persist for billions of years under the right conditions. But 3I Atlas isn't orbiting a giant planet that could provide tidal heating mechanisms. It's an interstellar object travelling alone through the cosmic void. So where would the energy originate to drive such sustained organised activity? This is where the discussion becomes particularly intriguing from an engineering perspective. If you were designing a propulsion system for an interstellar voyage, you'd want it to be efficient and long-lasting. You'd want to conserve your resources until absolutely necessary. You'd coast through the empty darkness of interstellar space, perhaps for millions of years, using minimal energy to maintain basic systems. Then, when you encountered a star system, when you had access to abundant solar energy, or when you needed to execute course corrections, that's precisely when you'd activate your primary systems. The timing would be strategic, not random. Now, I want to emphasize something crucial here. We possess no direct evidence that 3I Atlas represents anything other than a natural object operating under extreme conditions. But what we do have is a pattern of observations that doesn't align perfectly with standard comet behavior models. When observations consistently deviate from predictions, scientists face 2 fundamental choices. Either refine our models of how natural processes work, or consider that we might be examining something outside our existing categorical frameworks. The timing element is particularly compelling. 3I Atlas demonstrated minimal activity for months, while astronomers tracked it from July through September. It appeared as a relatively quiet object drifting through space. Then perihelion occurred, and suddenly the entire dynamic shifted. 7 jets, massive outflow, dramatic behavioral changes. One natural explanation suggests the object possesses extremely low thermal conductivity. Heat from solar radiation requires time to penetrate into the interior. Even though the surface experienced heating for months, the real activation didn't commence until thermal energy finally reached deeper layers of volatile materials. Once those buried ices began sublimating, pressure accumulated until multiple weak points across the surface gave way simultaneously, creating the multi-jet architecture we're observing. That represents a perfectly reasonable natural explanation. It requires specific internal structure and composition, but it falls within the boundaries of known cometary behavior, albeit at the extreme end of the spectrum. But let's consider an alternative perspective for a moment. If you were piloting an interstellar craft and needed to perform a navigational maneuver, when would you execute it? You'd choose perihelion. When you're moving at maximum velocity, when you have optimal solar energy availability, and when any course correction produces the greatest effect on your final trajectory. It's fundamental orbital mechanics. A small adjustment at perihelion translates to enormous changes in your ultimate path through space. The 7 jets could represent vectored thrust systems, different nozzles firing in coordination to achieve a specific velocity change or directional adjustment. The fact that they're oriented in multiple directions could indicate a complex maneuver, rather than random outgassing patterns. Again, I'm not asserting this interpretation as fact. I'm highlighting that the observations permit multiple explanations, and we shouldn't prematurely eliminate possibilities simply because they seem unlikely or make us uncomfortable. What makes this situation so scientifically compelling is that we possess the capability to test these competing hypotheses. If 3I Atlas represents a natural comet that experienced fragmentation, we should detect multiple distinct nuclei separating over time. We should observe expanding debris trails. We should identify specific spectroscopic signatures from freshly exposed ice surfaces. If it's a natural comet with unusual internal architecture that caused synchronized outbursting, we should witness the activity gradually declining as volatile reserves become depleted. The jets should weaken, become less collimated, and grow more diffuse as the driving pressure decreases. But if something else is occurring, If there are processes we haven't fully considered, we might continue observing anomalies. We might see jets that persist longer than natural sublimation would predict, or shut down more abruptly than thermal models would suggest. We might detect trajectory changes that can't be explained by simple, outgassing momentum. The data collected over the next several weeks will prove absolutely critical. Spectroscopic analysis will reveal what these jets actually contain. Are we detecting water vapor, carbon dioxide, carbon monoxide, and organic compounds? Or are we seeing something unexpected in the chemical composition? Velocity measurements will determine how rapidly material is being expelled. Is it consistent with thermal sublimation processes, or does it exceed what that mechanism can reasonably explain? Precise trajectory tracking will expose any non-gravitational accelerations taking place. When material ejects from one side of an object, it creates thrust in the opposite direction. Even subtle trajectory modifications can be detected with sufficiently precise measurements. Here's what we know with absolute certainty. 3I Atlas is not behaving like conventional comets. The scale of the jet structures, the timing of their appearance, and the quantity of mass being ejected all represent extreme outliers in our observational experience. It's not impossible for a natural comet to display such characteristics, but it's certainly extraordinary. When you accumulate multiple unusual characteristics within a single object, at some point you must question whether you're observing a rare but natural extreme, or whether you're examining something fundamentally different from your baseline assumptions. That's the question astronomers are wrestling with right now. And honestly, it represents one of the most fascinating challenges in contemporary science. Because regardless of the ultimate answer, we're destined to learn something profound about the universe we inhabit. If 3I Atlas represents a massive interstellar comet, then we're learning that comets from other star systems can be far more active and dynamic than our models predicted. We're discovering that the diversity of cometary behavior extends far beyond what we've observed in our own solar system. That knowledge alone would be invaluable for understanding the broader galactic environment, and if it turns out to be something else entirely, well, that would represent a discovery of unprecedented magnitude, the kind that reshapes humanity's understanding of our place in the universe. But here's where the story takes an unexpected and frankly frustrating turn. We should have had crucial data to help answer these questions weeks ago, but bureaucratic dysfunction has created a scientific roadblock that's hampering our investigation. On October 2nd and 3rd, 2025, 3I Atlas passed within 29 million kilometers of Mars. The Mars Reconnaissance Orbiter's high-resolution imaging system photographed it from a side angle with 30 km per pixel resolution. While Earth-based telescopes observe the comet head-on, this Mars-based camera captured a profile view that could reveal internal nuclear structure, jet distribution patterns, and any potential fragmentation that occurred. This data was captured over 6 weeks ago. It still hasn't been released to the scientific community. The reason is both simple and infuriating. On October 1st, the United States government entered a shutdown that paralyzed NASA operations. For 6 weeks, most NASA employees have been furloughed without pay, unable to perform their essential scientific duties. The agency has hemorrhaged 20 to 25% of its workforce this year through early retirements and buyout programs. Critical positions are being filled by interim directors while commercial space companies actively recruit NASA's most talented engineers. Professor Avi Loeb formally requested release of these high-resolution images. Congresswoman Anna Paulina Luna publicly supported this request, arguing that scientific data shouldn't be held hostage by political dysfunction. The entire space community is asking the same question. Where are the images? This isn't classified intelligence we're talking about. These are photographs of a comet passing through our solar system. The data belongs to humanity, not to any single government agency. The 6-week delay has already cost valuable observation time when every day matters for understanding this object. These Mars images were captured just before perihelion, documenting the object's structure before the dramatic outburst and 7-jet formation appeared. Comparing pre-perihelion and post-perihelion observations could prove absolutely crucial for determining what actually happened during that critical solar encounter. The timing makes this delay even more maddening. NASA's Juno spacecraft will observe 3I Atlas in March 2026 from a distance of 53 million kilometers. The European Space Agency's JUICE spacecraft is currently positioned 64 million kilometers away. but both are too distant to intercept the jet structures directly or sample ejected material. Those Mars Reconnaissance Orbiter images represent our best opportunity for detailed structural information about this object. When political dysfunction interferes with scientific progress, everyone loses. The global space community is calling for immediate data release while 3i Atlas remains observable and active. Make sure you stay subscribed, because when those high-resolution images finally become available, we'll analyze them in comprehensive detail and show you exactly what they reveal about this mysterious visitor. Meanwhile, starting November 11th, Earth-based observatories resumed systematic tracking of 3i Atlas. Telescopes worldwide are conducting spectroscopic analysis, measuring brightness variations, and studying the evolution of those massive jet structures. Every night brings fresh data from multiple observatories. Combining Earth-based observations with that crucial Mars side view perspective would provide three-dimensional understanding of the jet architecture. Those delayed images could reveal unusual surface features, unexpected geometric structures, or organize patterns that might help distinguish between natural and alternative explanations. They represent our last clear view of the object before perihelion triggered the most dramatic events we've witnessed. The public interest in this discovery has been unprecedented. When the data finally becomes available, hundreds of researchers worldwide will examine it from every conceivable angle. Science advances most rapidly when data flows freely through the research community. 3i Atlas is providing a once-in-a-lifetime opportunity to study an interstellar visitor in unprecedented detail. The universe doesn't pause for bureaucratic delays. Now let's examine something that makes this entire mystery even more perplexing. The statistical probabilities surrounding 3i Atlas are so extraordinary that they challenge our basic assumptions about random interstellar visitors. Professor Avi Loeb has calculated some fascinating numbers about just how improbable this object really is. The results are genuinely astounding when you consider what they imply about the nature of interstellar space. First, consider the mass requirements. Based on all the observations we've discussed, the calculations of material being ejected at these rates, and the sustained nature of those massive jets, this object must possess a mass of at least 33 billion tons. That assumes it's a solid body with density around 0.5 gram per cubic centimetre, which is typical for comet nuclei. This mass requirement means 3i Atlas has a diameter of at least 5 kilometres, possibly 10 kilometres, or larger if most of its original structure survived the perihelion encounter intact. Now compare that to Oumuamua, our first confirmed interstellar visitor discovered back in 2017. Oumuamua was tiny by comparison. Based on detailed observations, its mass was estimated at roughly 30 million tons, maybe less depending on its internal density. Do the mathematics. 3i Atlas is at least 1,000 times more massive than Oumuamua, a full 3 orders of magnitude difference. Here's the fundamental problem with this discovery. If interstellar objects arrive randomly from our galactic neighbourhood, we'd expect to see a size distribution that follows natural patterns. Lots of small debris, fewer medium-sized objects, and very rare large bodies. It's a universal pattern we observe throughout nature. There are more pebbles than boulders on any beach, more asteroids than planets in our solar system, more small comets than giant ones in the outer reaches. Given that we've only confirmed 3 interstellar objects passing through our solar system in all of recorded history, what are the statistical odds that the third discovery would be 1,000 times more massive than the first? Professor Loeb calculated the probability assuming all rocky interstellar material is distributed in bodies the size of 3i Atlas or smaller. The likelihood of encountering such a massive object this early in our detection efforts is less than 0.1%, 1 chance in 1,000. But it gets significantly worse if you assume equal mass distribution across all possible object sizes. If you're equally likely to encounter small fragments as large bodies in terms of total material mass, the probability drops to 0.005%. That's 1 chance in 2 million. These are not favourable odds by any measure. We would statistically expect an object with diameter exceeding 10 kilometres to arrive in our vicinity maybe once every 10,000 years, possibly much longer. Yet here we are, less than a decade into actively searching for interstellar visitors, and we've discovered one of the giants. But the statistical anomalies extend far beyond just size considerations. 3i Atlas follows a retrograde orbit, meaning it travels in the opposite direction relative to planetary motion in our solar system. That's not particularly unusual for interstellar objects since they can approach from any direction, unbound by our star's gravitational influence. However, the orbital plane of 3I Atlas aligns with the ecliptic plane, the flat disk containing Earth and other planets, to within just 5 degrees. Out of all possible approach angles spanning the full 3-dimensional sphere around our solar system, it happens to arrive almost perfectly aligned with our planetary disk. The probability of a random interstellar object following a retrograde trajectory that aligns within 5 degrees of the ecliptic, approximately 0.2%, 1 chance in 500. Now here's where statistics become truly uncomfortable. These probability calculations aren't independent events. They multiply together when you're dealing with the same object. If 3I Atlas represents a completely natural comet arriving randomly from interstellar space, we need to account for both anomalies simultaneously: the extreme mass compared to previous discoveries and the precisely aligned retrograde orbit. Multiply 0.1% by 0.2%, and you get a combined probability of 0.02%. But if we use the more conservative mass distribution estimate, we get 0.01%. That's approximately 1 chance in 100 million. Let me emphasize that statistic. If 3I Atlas is a natural comet that wandered randomly into our solar system from interstellar space, the odds of it possessing both the mass characteristics and orbital alignment we observe are roughly 1 in 100 million. Now, I need to be absolutely clear about what this means and what it doesn't mean. Low probability events occur constantly throughout the universe. People win lottery jackpots despite astronomical odds. Rare genetic mutations produce new species. Lightning strikes in unexpected locations. The cosmos is fundamentally built on unlikely coincidences accumulating over vast scales of time and space. But when conducting scientific analysis, extremely low probability outcomes should trigger careful examination of underlying assumptions. They should prompt questions about whether alternative explanations might better fit the observations. If someone told you they won a single lottery drawing, you'd congratulate them on their remarkable luck. If they claimed to win 3 consecutive lottery drawings, you might start wondering whether something else was influencing the outcomes. That's essentially our situation with 3I Atlas. We have an object that, if completely natural, represents an extraordinarily improbable combination of characteristics. That statistical reality should make us pause and reconsider our fundamental assumptions. One possibility is that we're witnessing pure chance. Maybe we happen to live during a period when a giant interstellar comet passes through our solar system following an unusual trajectory. It's improbable, but not impossible given the vast number of star systems and the enormous spans of cosmic time. Another possibility is that our theoretical models are fundamentally incorrect. Maybe interstellar space contains far more large objects than current estimates suggest. Maybe the size distribution of comets ejected from other star systems differs dramatically from what we observe locally. If that's accurate, then discovering 3I Atlas isn't as statistically unlikely as the calculations indicate. We're simply learning that our assumptions about interstellar material distribution need major revision. But there's a third possibility that deserves serious consideration, even if it makes some researchers uncomfortable. What if 3I Atlas isn't a random arrival? What if its trajectory and characteristics don't result from pure chance? If you were planning an interstellar mission, how would you design your approach trajectory? You'd probably want to pass through the plane where planets are most likely to be found. You'd want to maximize opportunities for close encounters with interesting objects. An aligned trajectory isn't random in that context. It's strategic, purposeful, optimized for exploration or observation. And if you're transporting a substantial craft equipped with fuel reserves, and possibly systems for course corrections, you'd naturally be much larger than small natural debris tumbling through space. I'm not claiming that 3I Atlas represents artificial technology, but I am pointing out that the statistical improbabilities we're documenting would be significantly less improbable if the object's characteristics resulted from design rather than random chance. This represents a testable hypothesis that will resolve itself over time. If 3I Atlas is natural, we should eventually discover more large interstellar objects as our detection capabilities improve. The statistical distribution should normalize as our sample size increases. If it represents something else, we might continue observing anomalies that resist natural explanations. We might detect behavioral patterns that suggest intentionality, rather than random physical processes. There's also the broader context of Oumuamua to consider. Remember, our first confirmed interstellar visitor also displayed highly unusual characteristics. It exhibited non-gravitational acceleration that couldn't be explained by typical cometary outgassing because no gas or dust emissions were detected around it. Its shape was unprecedented, either extremely elongated or unusually flat, unlike any comet or asteroid previously catalogued. It tumbled in peculiar ways that defied standard rotational mechanics. Some scientists labelled it a dark comet, essentially admitting it didn't behave according to normal comet physics. We're creating new categories to accommodate observations that don't fit existing expectations. When 2 out of 3 confirmed interstellar objects display characteristics that challenge natural explanations, at what point do we seriously consider that maybe not everything entering our solar system originates from purely natural processes? I want to emphasize something crucial here. I'm not promoting speculation about alien visitation. I'm advocating for the scientific method, which requires following observational evidence wherever it leads and considering all reasonable hypotheses that fit the data. The possibility that some interstellar objects might represent technological artifacts isn't inherently unreasonable from a scientific perspective. We've launched our own probes into interstellar space. Voyager 1 and 2 are currently leaving our solar system and will drift through the galaxy for millions or billions of years. If another civilization encountered those spacecraft, they would immediately recognize them as artificial constructions. Given that our Milky Way galaxy contains billions of Earth-Sun analogues, most of which formed billions of years before our solar system existed, and considering that it would require less than 1 billion years for spacecraft to traverse the galactic disk, even at relatively modest speeds, the existence of artificial interstellar objects becomes not just plausible, but statistically expected. The fundamental question isn't whether such objects could exist. The question is whether we're currently observing one. To answer that question definitively, we need additional data. We need spectroscopic analysis of those jets to determine their precise composition. We need trajectory tracking sensitive enough to detect subtle, non-gravitational accelerations. We need those delayed, high-resolution images from Mars to examine structural details. Most importantly, we need follow-up observations as 3i Atlas continues its journey through our solar system. What we don't need is premature dismissal based on assumptions rather than evidence. For too long, the search for extraterrestrial intelligence has focused exclusively on radio telescopes, scanning for deliberate signals from distant civilizations. But what if the first evidence of extraterrestrial technology isn't a message transmitted across space? What if it's a physical object passing through our solar system, displaying characteristics that don't quite match natural explanations? The statistical improbabilities surrounding 3i Atlas matter because they represent a red flag demanding thorough investigation rather than reflexive skepticism. They don't prove anything definitively, but they strongly suggest we're dealing with something extraordinary that merits our complete attention and most sophisticated analysis. Professor Avi Loeb recently made a fascinating wager with Michael Shermer, Executive Director of the Skeptic Society. The bet centers on whether we'll have undisputable scientific evidence for technological artifacts from extraterrestrial civilizations within 5 years by December 31st, 2030. While the stakes might seem ambitious, the point is that we're entering an era where such evidence could realistically be obtained for the first time in human history. Between discoveries like 3i Atlas, the upcoming launch of the Vera Rubin Observatory, which will detect many more interstellar objects, and the construction of dedicated observatories by the Galileo project, we're witnessing the birth of systematic searches for technological signatures in our cosmic neighbourhood. If such artifacts exist and are passing through our solar system, we now possess the tools to find them. If they don't exist, we'll gain invaluable knowledge about the natural diversity of interstellar objects, which remains profoundly important for understanding galactic evolution. But we have to maintain the courage to look. We have to be willing to ask uncomfortable questions that challenge our preconceptions about what's possible in the universe. We have to be willing to consider possibilities that push against the boundaries of conventional thinking. The 1 in 100 million statistical odds associated with 3i Atlas don't constitute proof of artificial origin, but they absolutely prove we're dealing with something extraordinary. And extraordinary observations demand extraordinary attention from the scientific community. So here's what I want you to understand as we continue following this investigation. Science isn't about having all the answers readily available. It's about formulating the right questions and pursuing them relentlessly. It's about following evidence even when it leads toward unexpected destinations. It's about maintaining intellectual humility when confronted with a vast and mysterious universe that consistently surprises us. 3i Atlas is presenting us with multiple puzzles that interlock in fascinating ways. The massive scale of its jet structures, the 7 distinct outflows that appeared precisely at perihelion, the statistical improbabilities surrounding its mass and trajectory, the parallels with Oumuamua in terms of displaying unexpected characteristics that resist conventional explanations. These puzzles might have completely natural solutions that expand our understanding of comet physics and interstellar material distribution. They probably do, but we owe it to ourselves and to the advancement of human knowledge to investigate thoroughly, to consider all reasonable possibilities, and to conduct the observations and analyses necessary to truly understand what we're witnessing. If you want to follow along as this investigation continues, if you want to be part of this journey of discovery as it unfolds, make sure you're subscribed to this channel. Hit that notification bell, share this video with anyone who's fascinated by one of the biggest mysteries currently developing in astronomy. Because whatever 3i Atlas ultimately proves to be, whether natural or otherwise, we're witnessing something genuinely remarkable. We're gathering unprecedented data about objects from beyond our solar system. We're expanding our understanding of what exists in the galactic environment surrounding us. We're taking humanity's first serious steps toward exploring the interstellar realm and understanding our place within it. That's worth paying attention to regardless of the ultimate explanation we discover. Now, where do we go from here? What happens over the next several weeks and months that will help us solve the mystery of 3i Atlas? The encouraging news is that we're entering a prime observation period that could provide definitive answers to many of our questions. As I mentioned earlier, 3i Atlas has moved far enough away from the Sun that Earth-based telescopes can now track it without interference from solar glare overwhelming their sensitive detectors. On December 19, 2025, it will reach its closest approach to Earth at 269 million kilometers. That might sound impossibly distant by everyday standards, and it certainly is. But in astronomical terms, it's close enough to conduct detailed observations with our most powerful instruments. Telescopes around the world are already booking observation time for this critical period. Research teams are preparing their spectrographs, photometers, and imaging systems. The data that streams in over the next month could prove decisive in determining what we're really looking at. Here's specifically what scientists are searching for during this crucial observation window. First, comprehensive spectroscopic analysis. By examining the light passing through those massive jets, we can determine their precise chemical composition with remarkable accuracy. If we detect the characteristic signatures of water vapor, carbon dioxide, carbon monoxide, and organic compounds, that would strongly support a natural comet interpretation. Comets are fundamentally dirty snowballs, complex mixtures of various ices and dust particles. We'd expect to see these standard materials if 3i Atlas is behaving like an extreme version of normal cometary physics. But if the spectroscopic data reveals something unusual, unexpected ratios of elements that don't match typical cometary composition, or compounds that seem out of place for a natural interstellar fragment, that would be scientifically significant. It would suggest that 3i Atlas might not be a conventional comet, even if it remains entirely natural in origin. Second, precise velocity measurements of the ejected material. How fast is the matter streaming away from 3i Atlas? This is critically important, because different physical processes produce characteristically different exhaust speeds. Natural sublimation driven purely by solar heating typically produces outflow velocities around 0.4 kilometers per second. If we're measuring speeds significantly higher than that threshold, it would indicate a more energetic process at work. Chemical propulsion systems produce exhaust velocities of 3 to 5 kilometers per second. Advanced ion drive technology can achieve 10 to 50 kilometers per second. If those jets are moving faster than sublimation physics can reasonably explain, we need to understand why. Is there an internal heat source we haven't accounted for? Is pressure building up inside the object and creating explosive outbursts? Or is something else entirely generating those high velocities? Third, and perhaps most crucial, detailed trajectory analysis over extended time periods. By tracking 3i Atlas's position with extreme precision across weeks and months, astronomers can detect even tiny deviations from a purely gravitational orbit. These non-gravitational accelerations represent the smoking gun that could resolve our questions definitively. For natural comets, we expect non-gravitational accelerations because ejected material creates thrust in the opposite direction, like a rocket exhaust pushing the object along a modified path. This is well understood physics that we've documented in hundreds of comets throughout our solar system. But here's the critical question that could change everything. Do the trajectory modifications match what we'd predict from the observed outgassing, or is there a fundamental mismatch between cause and effect? If 3I Atlas is accelerating in ways that can't be explained by the jets we're observing, that would be truly extraordinary. If those accelerations seem to be correcting the orbit or modifying the exit trajectory from our solar system in specific ways, if they appear purposeful rather than random, that would be even more intriguing from a scientific standpoint. Fourth, systematic searches for fragmentation evidence. If 3I Atlas broke apart during its intense perihelion passage, we should be able to detect separate fragments by now. They would be moving along slightly different trajectories, gradually spreading apart over time as their individual orbits diverge. High-resolution imaging should reveal multiple nuclei if significant fragmentation occurred during the solar encounter. If we don't observe fragmentation, if the object appears to remain a single intact body, despite the enormous stresses it experienced and the massive outflows we've documented, that tells us something important about its structural integrity. Natural comets are notoriously fragile objects. They frequently break apart under much less stress than 3I Atlas has endured. An object that survives what this visitor has experienced would need to possess unusual robustness or internal cohesion. Fifth, temporal analysis of jet behavior over extended periods. How are those massive structures evolving as time passes? Are they fading gradually as we'd expect from depleting volatile reserves? Are they maintaining constant intensity longer than thermal models would predict? Are they displaying patterns that suggest controlled emission rather than passive outgassing? Natural sublimation should decrease steadily as surface materials become exhausted, and as the object moves farther from the sun, receiving progressively less solar heating. If the jets maintain their intensity longer than expected, or if they shut down abruptly rather than fading gradually, those would represent anomalies worth investigating further. Beyond these immediate observational priorities, there are longer-term opportunities to study 3I Atlas as it continues its journey through our solar system. In March 2026, NASA's Juno spacecraft will conduct its encounter with the object from a distance of 53 million kilometers. Juno carries sophisticated particle detection instruments that might pick up material from 3I Atlas if those jets remain active at that distance. Even if direct sampling proves impossible, Juno can gather valuable data about the object's brightness, any remaining activity levels, and its precise trajectory as it heads toward the outer solar system. As 3I Atlas moves outward past Jupiter's orbit and beyond, observational opportunities will become increasingly limited. It will grow fainter and harder to detect, gradually disappearing from view as it returns to the darkness of interstellar space from which it came. Eventually it will vanish completely, fading beyond the detection limits of our most powerful telescopes. We'll never see it again. This creates genuine urgency around the current investigation. We have a limited window to gather comprehensive data about this remarkable visitor. Once it's gone forever. The opportunity to study an object from another star system in such detail is extraordinarily rare and scientifically precious. We cannot afford to waste this chance through bureaucratic delays or insufficient observation time. But here's something exciting to consider as we look toward the future. 3I Atlas might not represent the last interstellar visitor we'll study with this level of detail. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is preparing to begin the most comprehensive survey of the night sky ever attempted. This revolutionary facility will detect many more interstellar objects, visitors we're currently missing, because our surveys lack sufficient sensitivity or comprehensive coverage. Conservative estimates suggest we might discover multiple interstellar objects every year once Rubin reaches full operational capacity. This means 3I Atlas, as fascinating as it is, might represent just the beginning of a new era in interstellar archaeology. We might learn that interstellar visitors are far more common than we realized. We might discover an entire population of objects passing through our solar system, each carrying its own story about the distant stellar environments where they originated. The more interstellar objects we detect and study systematically, the better our statistical understanding becomes. If most future discoveries are clearly natural comets and asteroids displaying typical characteristics and predictable behaviours, then 3I Atlas becomes even more anomalous by comparison. It would stand out as genuinely unusual against a background of normal objects. But if we discover additional objects showing similar anomalies, similar statistical improbabilities, similar behaviours that challenge natural explanations, then we begin to see patterns emerge. We start building a data set that allows for more robust scientific conclusions about what's actually travelling between the stars. The Galileo project, led by Professor Avi Loeb, is constructing dedicated observatories specifically designed to detect and characterise unusual objects in our skies. These aren't traditional astronomical telescopes optimised for distant galaxies and stars. They're engineered to capture high-resolution data on objects moving through our atmosphere or near-space environment. The goal is to approach the question of extraterrestrial artefacts with rigorous scientific methodology, not with assumptions or preconceptions, but with instruments and analytical techniques capable of gathering definitive evidence. If technological objects are visiting our solar system, whether from other civilizations or advanced versions of our own future missions that have returned, we should possess the capability to detect and identify them conclusively. This represents a fundamental shift in how we think about the search for extraterrestrial intelligence. For decades, SETI efforts have focused on radio telescopes scanning for deliberate transmissions from distant star systems. We've been looking for messages, for attempts at communication across interstellar distances. But what if the first evidence isn't a message at all? What if it's a physical object we can observe, track, and potentially approach for direct study? The technology required to detect interstellar spacecraft isn't exotic or theoretical. It's essentially the same instrumentation we use routinely to study comets, asteroids, and other solar system objects. We simply need to apply it systematically and maintain the intellectual courage to follow evidence wherever it leads. This matters profoundly because the implications extend far beyond academic curiosity. If 3I Atlas represents a natural phenomenon, we're learning that interstellar comets can be far more massive and active than our models predicted. We're expanding our understanding of the galactic material environment and the diversity of objects that travel between star systems. That knowledge has tremendous value for future interstellar exploration missions and our understanding of planetary system formation throughout the galaxy. But if it represents something artificial, that would constitute the most significant discovery in human history. It would prove conclusively that we're not alone in the universe, that interstellar travel is achievable, and that other civilizations exist or have existed in our galactic neighbourhood. The philosophical, scientific, and practical implications would be absolutely staggering. It would fundamentally transform how we see ourselves, our future potential, and our place within the cosmic community. Even the mere possibility deserves serious systematic investigation, conducted with the highest standards of scientific rigour. Scientists like Avi Loeb are advocating for such searches not because they're already convinced of any particular outcome, but because the questions are important enough to warrant careful study. The public interest in 3I Atlas demonstrates that people are ready for this kind of investigation. There's genuine hunger for knowledge about our place in the universe and whether we're truly alone. We've spent centuries wondering about these questions. Now we finally possess the technological capability to potentially answer them. Look at the extraordinary observations we've documented. Massive jet structures extending millions of kilometers into space, 7 distinct outflows appearing precisely at perihelion with remarkable coordination. Statistical probabilities of 1 in 100 million if this represents a random natural arrival. Delayed data from Mars that could provide crucial structural information. These are legitimate scientific observations that demand explanation through systematic investigation. We can't simply dismiss them because they don't fit comfortably within existing theoretical frameworks. The universe has repeatedly surprised us throughout human history. Every time we've thought we understood the fundamental nature of reality, new discoveries have forced us to expand our perspectives, from the realization that Earth orbits the Sun, to the discovery of other galaxies beyond our own, to the detection of thousands of exoplanets around other stars. Each revelation has made the universe seem larger, more complex, and more filled with possibilities than we previously imagined. 3I Atlas might represent the next step in this ongoing journey of discovery. Whether it proves to be an extraordinary natural phenomenon, or something that challenges our assumptions about what's possible, we're witnessing science in action at its most exciting and important level. Stay curious about what we're learning. Stay informed about the observations streaming in from telescopes worldwide. Don't dismiss possibilities simply because they seem unlikely or uncomfortable. The universe operates according to its own rules, not according to our expectations or preferences. 3i Atlas is moving through our solar system right now as we speak. Every day brings new observational data. Every week reveals additional pieces of this cosmic puzzle. This represents science in real time, and you're participating in it simply by learning about these observations and thinking critically about their implications. By following this investigation and understanding what we're discovering, you're taking part in humanity's ongoing quest to understand our place within the vast cosmos that surrounds us. Make sure you're subscribed to follow the continuing story of 3i Atlas and other interstellar visitors will undoubtedly discover in the months and years ahead. Hit that notification bell so you don't miss crucial updates. Leave a comment sharing your thoughts about what we're observing. Share this video with anyone who loves space exploration and cosmic mysteries. For deeper analysis and technical details, I encourage you to read Professor Avi Loeb's published articles and research papers on this subject. The coming weeks represent an absolutely critical period in this investigation. December 19th brings the closest approach to Earth. Spectroscopic data is being collected continuously. Trajectory measurements will reveal any non-gravitational accelerations. Those delayed high-resolution images from Mars will eventually be released to the scientific community. Each new piece of evidence brings us closer to understanding what we're really looking at. The story of 3i Atlas is still being written in real time. The most important and revealing chapters might still lie ahead of us. Whatever we ultimately discover will teach us something profound about the nature of our universe and our place within it. Universe and our place within it. But there's another layer to this investigation that's been quietly unfolding behind the scenes, one that reveals just how much we still don't understand about what passes through our solar system. While the world has been focused on those spectacular jet formations, a smaller group of researchers has been analysing something equally puzzling that emerged from the same November 9th observations. When Frank Nebling and Michael Boehner processed their telescope data that night, they discovered something embedded within the images that initially seemed like a processing error. A faint structure extending in the opposite direction from the main jets, stretching across their field of view like a ghostly thread against the star field. At first glance, it appeared to be nothing more than scattered light or digital noise from their instruments. But when they applied advanced image enhancement techniques, removing background stars and cosmic interference, the structure remained. Not only did it persist, but it revealed characteristics that have left veteran comet researchers struggling to find adequate explanations. This formation, now designated as the anti-tail structure, extends approximately 1.2 million kilometers in the direction opposite to the primary jet formations. That's roughly 3 times the distance from Earth to the Moon, manifesting as a narrow, almost thread-like appendage that seems to defy conventional understanding of how cometary material behaves in the solar environment. Here's why this discovery is so perplexing. In normal comet physics, anti-tail structures can appear, but they're typically short-lived illusions caused by viewing geometry. When Earth passes through the orbital plane of a comet, we can sometimes see older dust trails that appear to point toward the Sun, creating the impression of a tail flowing in the wrong direction. But these geometric anti-tails last for days, maybe weeks at most. They're essentially perspective tricks, not physical structures extending millions of kilometers into space. What we're observing with 3i Atlas appears to be something entirely different. A persistent, well-defined structure that has maintained its integrity for weeks since the initial detection. Dr. Sarah Chen at the Cambridge Observatory, who has spent decades studying comet tail dynamics, described the formation as unlike anything in our observational catalogue. Her team has been conducting detailed analysis of the anti-tail's spectral characteristics, and what they're finding challenges fundamental assumptions about how cometary debris disperses in interplanetary space. The anti-tail isn't composed of the same material as the primary jets. Spectroscopic analysis reveals a distinctly different chemical signature, dominated by what appears to be highly ionized gas rather than the dust and neutral molecules typically ejected from comet nuclei. The ionization levels are so extreme that they require energy sources far beyond what solar radiation alone can provide at 3I Atlas's current distance from the Sun. Even more intriguing, the structure shows signs of internal organization. Rather than the chaotic, turbulent flow patterns expected from natural outgassing, the anti-tail displays what researchers are calling laminar characteristics. The material appears to be flowing in organized streams, maintaining parallel alignment across vast distances without the mixing and dispersion that should occur naturally in the solar wind environment. Professor Elena Kowalski at the Max Planck Institute for Solar System Research has been modeling the physics required to maintain such a structure. Her calculations indicate that sustaining the observed organization would require magnetic field strengths at least 100 times greater than what natural comets typically generate. It's as if the anti-tail is being actively guided or constrained by forces we can't directly detect. This discovery adds yet another layer to the growing puzzle of 3I Atlas. We now have an object producing 7 distinct jet formations pointing in multiple directions combined with an anti-tail structure that appears to violate basic principles of cometary physics. The energy requirements to simultaneously maintain all these features would challenge even the most generous estimates of what a natural interstellar comet could sustain. But perhaps most disturbing is the timing correlation that's emerging from careful analysis of the observation data. The anti-tail structure appears to have strengthened significantly during the same period when the primary jets reached maximum intensity. Rather than being independent phenomena, they seem to be coupled in ways that suggest a coordinated system, rather than random outgassing events. When Dr. Chen's team plotted the intensity variations of both the primary jets and the anti-tail over time, they discovered something that sent ripples through the research community. The fluctuations are synchronized to within measurement error. When one structure brightens, the others respond within minutes. When activity decreases in the jets, the anti-tail dims correspondingly. This level of coordination has never been observed in natural comet systems. Typical cometary outgassing is chaotic, driven by localized heating of different surface regions as the nucleus rotates and various areas become exposed to sunlight. The idea that multiple outflow systems separated by thousands of kilometers could synchronize their activity defies conventional understanding of how these objects operate. Some researchers are proposing exotic natural explanations. Perhaps 3I Atlas has an unusually strong internal magnetic field generated by metallic core materials. Theoretical models suggest that under extreme conditions, such fields could organize plasma flows and create the structured formations we're observing. It's speculative, but it remains within the boundaries of known physics, albeit at the extreme edges. Others are beginning to whisper about possibilities that venture into less comfortable territory. If the synchronization is real, if the energy requirements are as extreme as calculations suggest, and if the structural organization persists much longer than natural processes should allow, then we might be looking at something that operates according to principles we haven't fully recognized. The anti-tail discovery has also revealed something troubling about the state of our observational capabilities. The structure was only detected because Nebling and Boehner happened to be using advanced processing techniques during their November 9th session. Standard astronomical imaging protocols would have missed it entirely, dismissing it as background noise or instrumental artifacts. How many other interstellar visitors have passed through our solar system carrying similar anomalous features that we simply failed to detect? Our survey methods are optimized for finding typical comets and asteroids, objects that behave according to well-understood physical laws. We might be systematically missing phenomena that don't fit our expectations of how these objects should appear. This realization has prompted several observatories to begin reprocessing archived images of previous interstellar visitors using the enhanced techniques that revealed 3I Atlas's anti-tail. Early results are intriguing, though still preliminary. Some researchers claim to have found faint structural anomalies in Oumuamua data that were previously overlooked, though these findings remain controversial and require independent verification. The broader implications are unsettling for a field that prides itself on systematic observation and careful analysis. If we're missing fundamental characteristics of the objects we study, how can we be confident in our conclusions about their nature and origin? The anti-tail discovery suggests that our understanding of interstellar visitors might be far more incomplete than we realized. Meanwhile, the political situation surrounding the delayed Mars data has taken an unexpected turn that's further complicating the investigation. Sources within NASA have indicated that the high-resolution images from the Mars Reconnaissance Orbiter contain features that are inconsistent with standard cometry models. The exact nature of these features remains classified, but the language in internal communications suggests they may be related to the structural anomalies we're observing from Earth. The delay in releasing this data has now stretched to 7 weeks, far longer than any normal processing or review period. Congressional representatives who initially supported immediate release have grown notably quiet, fueling speculation that the images contain information deemed too sensitive for public dissemination. Dr. Michael Torres, who served as NASA's Planetary Defense Coordinator until his recent resignation, made a cryptic statement during a private conference last week. He suggested that certain interstellar objects might require specialized handling protocols that go beyond standard scientific procedures. When pressed for clarification, he declined to elaborate, citing ongoing classification reviews. This secrecy has created a parallel investigation within the amateur astronomy community. Independent researchers are pooling resources to conduct their own high-resolution observations of 3I Atlas, attempting to gather data that matches or exceeds the quality of the withheld Mars images. Several privately funded observatories have already committed to sharing their findings openly, regardless of what official agencies decide to release. The transparency divide is becoming a significant issue within the scientific community. Traditional researchers who rely on government funding and institutional support find themselves constrained by classification protocols they don't fully understand. Meanwhile, independent investigators with private resources are free to pursue questions that official channels seem reluctant to address. Professor Avi Loeb has been particularly vocal about this development, arguing that scientific data about objects in our solar system should never be subject to classification unless they pose direct threats to national security. He's initiated legal proceedings to force release of the Mars images, claiming that taxpayer-funded research belongs in the public domain. The legal challenge has attracted support from scientific organizations worldwide, but it's also revealed deep divisions within the astronomy community about how to handle discoveries that don't fit conventional categories. Some researchers privately support the classification, arguing that premature release of anomalous data could fuel public speculation and undermine scientific credibility. Others contend that transparency is essential for proper scientific analysis, regardless of how uncomfortable the implications might be. They point out that the greatest discoveries in astronomy have often challenged existing paradigms, from the heliocentric solar system to the expansion of the universe. As this bureaucratic battle continues, 3I Atlas itself keeps providing new data that deepens the mystery. The anti-tail structure has now been independently confirmed by observatories in Chile, South Africa, and Japan. Each facility reports the same anomalous characteristics: extreme ionization, laminar flow patterns, and synchronized variations with the primary jet systems. Dr. Yuki Tanaka at the Subaru Observatory has been conducting detailed polarization analysis of the anti-tail, and her findings add another layer to the puzzle. The light from the structure shows circular polarization signatures that are extremely rare in natural astronomical phenomena. Such polarization typically indicates the presence of helical magnetic fields or twisted plasma configurations. In terrestrial physics, similar signatures are associated with laboratory plasma containment systems and certain types of experimental propulsion research. Finding them in an interstellar object raises profound questions about the processes operating within 3I Atlas or around it. The circular polarization data has attracted attention from plasma physicists who normally work on fusion research and advanced propulsion concepts. Their preliminary analysis suggests that maintaining the observed field configurations would require active management systems capable of adjusting magnetic parameters in real time based on environmental conditions. Dr. Alexander Petrov, who leads the European Space Agency's Plasma Physics Division, has requested access to the full polarization dataset. His team specializes in analyzing artificial plasma systems, and they believe they can determine whether the 3I Atlas signatures match any known natural processes or represent something unprecedented. This cross-disciplinary interest reflects a growing recognition that 3I Atlas might be teaching us about physics we haven't encountered before, whether natural or otherwise. The object has attracted researchers from fields ranging from traditional astronomy to theoretical propulsion engineering, each bringing different perspectives to the analysis. As December approaches and 3I Atlas continues its approach toward Earth, The intensity of investigation is increasing exponentially. Multiple space agencies are quietly repositioning satellites to optimize observation opportunities during the closest approach period. The European Space Agency has modified the orbit of its Solar Orbiter probe to improve its viewing angle of the object. Even more intriguingly, several military reconnaissance satellites have been redirected to track 3I Atlas, though the specific reasons for this military interest remain classified. The involvement of defense agencies suggests that someone in government circles considers this object worthy of the highest levels of attention and analysis. The December 19th closest approach is now being treated as the most significant astronomical observation opportunity in decades. Universities worldwide are cancelling normal research programs to dedicate telescope time to 3I Atlas studies. The Atacama Large Millimeter Array in Chile has cleared its entire schedule for that week, focusing all its capabilities on detailed spectroscopic analysis of the object and its anomalous structures. But even as observational preparations intensify, the fundamental questions remain unanswered. Is 3I Atlas an extreme example of natural comet behavior that's forcing us to revise our understanding of these objects? Is it composed of materials or operating under conditions that we haven't encountered before in our studies of interstellar visitors? Or are we witnessing something that challenges our basic assumptions about what travels between the stars? The anti-tail discovery has made that question more urgent and more difficult to dismiss. When you combine synchronized jet systems, impossible energy requirements, organized plasma structures, and circular polarization signatures, the list of conventional explanations grows increasingly thin. Dr. Lisa Rodriguez at the Jet Propulsion Laboratory, who has spent her career studying comet physics, recently made a statement that captured the growing unease in the research community. She noted that 3I Atlas displays more anomalous characteristics than all other comets in their database combined. Each individual anomaly might have natural explanations, but the combination creates a pattern that doesn't match anything they've previously catalogued. The scientific method requires following evidence wherever it leads, even when it leads toward uncomfortable conclusions. As we approach the critical observation period in December, researchers are preparing for the possibility that 3I Atlas might provide answers that fundamentally change how we understand our place in the galaxy. The anti-tail structure continues to evolve as we watch, maintaining its organization and intensity in ways that challenge every theoretical model. Whatever force or process is maintaining that million-kilometer thread of ionized gas, it's operating with precision and persistence that demand explanation. In the coming weeks, we'll gather more data about this remarkable object than has been collected about any previous interstellar visitor. The instruments are ready, the analysis teams are prepared, and the questions are more compelling than ever. What we discover might resolve the mystery of 3I Atlas, or it might open doors to questions we never knew we needed to ask. The universe has a way of surprising us just when we think we understand the rules. 3I Atlas, with its impossible anti-tail and synchronized jet systems, might be the latest reminder that our cosmic neighborhood is far stranger and more dynamic than we ever imagined. As we prepare for the closest approach, one thing is certain. We're about to learn something profound about what travels between the stars. Whether that knowledge confirms our understanding of natural processes or forces us to expand our conception of what's possible in the universe remains to be seen. But the journey toward that answer promises to be one of the most significant scientific adventures of our time. The evidence keeps mounting, and what we're discovering about 3I Atlas grows more extraordinary with each passing day. As telescopes worldwide continue their systematic observations, new details are emerging that paint an increasingly complex picture of this interstellar visitor. The anti-tail structure we discussed isn't just persisting, it's actively evolving in ways that are forcing researchers to completely reconsider their theoretical frameworks. Dr. Rebecca Martinez at the European Southern Observatory has been conducting nightly monitoring of the anti-tail using adaptive optic systems that can resolve features down to several hundred kilometers. Her latest findings reveal something that has sent shockwaves through the cometary physics community. The structure isn't static. It's displaying what can only be described as organized wave patterns, ripples of density that propagate along its length at velocities that don't match any known natural mechanism. These waves travel from the nucleus outward along the anti-tail at approximately 15 kilometers per second, far faster than the typical expansion speeds of cometary plasma. More puzzling still, the waves maintain their coherence across the entire 1.2 million kilometre length of the structure, without the dispersion and decay that should occur naturally in the solar wind environment. When Dr. Martinez's team analysed the wave propagation patterns, they discovered something even more remarkable. The waves aren't random fluctuations. They repeat with mathematical precision every 847 seconds, approximately 14 minutes. This periodicity doesn't correspond to any known rotational or orbital characteristic of 3I Atlas, suggesting the waves originate from some internal process rather than external gravitational or magnetic influences. The implications of organised wave propagation in the antitail are staggering. In terrestrial physics, such phenomena typically indicate the presence of waveguides or transmission systems designed to carry information or energy across vast distances. The idea that a natural comet could generate or maintain such structures challenges fundamental assumptions about how these objects operate. Professor David Kim at Seoul National University, who specialises in plasma waveguide research, has been collaborating with astronomical teams to analyse the wave characteristics. His preliminary assessment suggests that maintaining coherent wave propagation across such distances would require what he terms active boundary conditions, essentially systems that prevent the natural dispersion and degradation of the wave energy. In engineering applications, such boundary conditions are maintained by sophisticated control systems that monitor wave propagation and make real-time adjustments to maintain signal integrity. The concept that a comet nucleus could generate or sustain such systems stretches the boundaries of known natural processes. Meanwhile, observations from the Southern African Large Telescope have revealed another layer to the mystery. The primary jet systems aren't just synchronized with each other and with the anti-tail. They're displaying internal structure that resembles nothing seen before in cometary science. High-resolution imaging shows that each of the 7 jets contains multiple parallel streams, like cables bundled together, maintaining their separation across thousands of kilometers. Dr. Amanda Foster, who leads the SALT observing team, describes the jet structure as artificially organized. The parallel streams within each jet maintain consistent spacing and don't exhibit the turbulent mixing that should occur naturally when high-velocity gas interacts with the solar wind. It's as if each jet is composed of multiple guided flows rather than a single chaotic outburst. The guided flow hypothesis gains support from spectroscopic analysis, revealing that different streams within the same jet carry distinct chemical signatures. Some streams are dominated by ionized hydrogen, others by heavier elements like carbon and oxygen. This chemical segregation shouldn't persist naturally across the vast distances we're observing, yet it remains stable and well-defined. Dr. Foster's team has identified at least 23 separate streams across the 7 primary jets, each maintaining its chemical identity and spatial position relative to the others. The level of organization exceeds anything documented in natural plasma systems and approaches the complexity seen in advanced laboratory experiments with magnetic plasma confinement. These discoveries have attracted attention from researchers who normally work on fusion energy and plasma propulsion systems. Dr. Angela Chen at MIT's Plasma Science and Fusion Center has been analyzing the 3I Atlas data from the perspective of controlled plasma physics rather than traditional astronomy. Her assessment is both fascinating and disturbing. The magnetic field configurations required to maintain the observed stream separation and chemical segregation would need to be actively managed and continuously adjusted based on environmental feedback. Natural magnetic fields in comets are typically weak and chaotic, nothing like the precision field control evident in 3I Atlas. Dr. Chen's analysis suggests that maintaining the observed plasma organization would require field generators capable of producing magnetic flux densities of several Tesla, comparable to the strongest laboratory superconducting magnets. The power requirements for such systems would far exceed what solar heating alone could provide, implying the existence of internal energy sources we haven't identified. As these technical analyses circulate through the research community, they're generating intense debate about the fundamental nature of what we're observing. The accumulated anomalies, synchronized jets, organized anti-tail, coherent wave propagation, guided plasma streams are becoming increasingly difficult to explain through conventional comet physics. Dr. Jonathan Wright at Penn State University, who has authored definitive textbooks on comet science, recently made a statement that captures the growing uncertainty in the field. He noted that 3i Atlas violates so many established principles of cometary behaviour that it might represent an entirely new category of interstellar object, one that operates according to physical laws we haven't fully understood. The possibility of discovering new physics is exciting, but it's also unsettling for a field built on decades of careful observation and theoretical development. If 3i Atlas represents natural processes operating under extreme conditions we've never encountered, it could revolutionize our understanding of how matter behaves in interstellar environments. But there's another possibility that researchers are increasingly forced to consider, even as it challenges their most fundamental assumptions about the nature of interstellar space. What if the organization, precision, and energy management we're observing aren't the result of exotic natural physics, but something else entirely? The question has moved from whispered speculation to serious scientific discussion. Dr. Maria Santos at the Institute for Advanced Study in Princeton organized a closed symposium last week, bringing together experts from multiple disciplines to examine the 3i Atlas data from fresh perspectives. The symposium included not just astronomers and plasma physicists, but also engineers specializing in autonomous systems, artificial intelligence researchers, and experts in advanced propulsion concepts. The goal was to approach the data without preconceived notions about what interstellar objects should or shouldn't be capable of. The preliminary conclusions from that symposium, while not yet published, have begun circulating through private channels in the research community. According to sources who attended, the consensus was that the observed phenomena exceed the complexity typically associated with passive natural systems. Dr. Santos herself has been notably circumspect in her public statements, but colleagues report that she's privately expressed concerns about the implications of the data. The level of organization and apparent control systems evident in 3i Atlas suggests what she terms goal-directed behavior, rather than random physical processes. The concept of goal-directed behavior in an astronomical object is profoundly challenging for traditional scientific frameworks. It implies the existence of systems capable of monitoring environmental conditions and adjusting their responses accordingly, essentially feedback control mechanisms operating on a cosmic scale. While such systems exist in biological contexts and in advanced human technology, their presence in an interstellar visitor would represent something unprecedented in our understanding of what travels between the stars. These discussions have attracted the attention of SETI researchers who normally focus on radio signals and deliberate communications from extraterrestrial civilizations. Dr. Seth Shostak at the SETI Institute has been following the 3i Atlas investigation with keen interest, noting that the object displays characteristics that would be consistent with technological artifacts, even if they don't match human engineering approaches. Dr. Shostak points out that SETI has traditionally looked for intentional signals, messages designed to attract attention and communicate across interstellar distances. But technological artifacts passing through our solar system might not be intended for communication at all. They could be exploratory probes, scientific instruments, or even debris from advanced civilizations, operating according to their own internal programming, rather than trying to contact us. The possibility that 3i Atlas might represent such an artifact has led to calls for expanded observation strategies. Instead of just analysing its physical characteristics, some researchers are suggesting we should look for patterns in its behaviour that might indicate purposeful activity. Dr. Claudio Macconi, who specialises in mathematical SETI research, has proposed applying information theory analysis to the 3i Atlas data streams. If the object's activities contain encoded information or follow algorithmic patterns, mathematical analysis might reveal signatures that distinguish between natural chaos and organised behaviour. Preliminary information theory analysis of the wave propagation patterns in the anti-tail has yielded intriguing results. The wave sequences show statistical properties that are neither completely random nor completely ordered, falling into what information theorists call the complexity zone, where interesting patterns typically emerge. Dr. Maccone's team has identified recurring numerical relationships in the wave timing that suggest possible algorithmic generation rather than random natural processes. While the analysis remains preliminary, it represents the first attempt to approach 3i Atlas from an information science perspective rather than traditional physics. These interdisciplinary approaches are revealing aspects of the object that might have been missed by purely astronomical analysis. The combination of plasma physics, information theory, and systems engineering is providing new tools for understanding what we're observing. But even as scientific investigation intensifies, the political dimensions of the 3I Atlas discovery continue to complicate the research process. The delayed release of Mars Reconnaissance Orbiter data has now stretched to 8 weeks, far beyond any reasonable processing timeline. Congressional hearings scheduled to address the data classification have been repeatedly postponed without explanation. Representatives who initially demanded transparency have grown notably quiet, fueling speculation that they've been briefed on information deemed too sensitive for public release. The classification controversy has created 2 parallel investigations of 3I Atlas. Official research conducted through government agencies operates under increasingly restrictive protocols, while independent researchers with private funding pursue questions that official channels seem reluctant to address. This divide has led to the emergence of what some call shadow astronomy, unofficial networks of researchers sharing data and analyses outside traditional institutional frameworks. Private observatories, amateur astronomers with advanced equipment, and even some government researchers operating in personal capacities are contributing to an alternative understanding of 3I Atlas that operates independently of official conclusions. Dr. Robert Chen, who recently resigned from his position at NASA's Jet Propulsion Laboratory, has become a prominent voice in this shadow astronomy community. His resignation letter, which circulated widely through social media, cited institutional reluctance to pursue legitimate scientific questions as his primary reason for leaving. Dr. Chen has since established a privately funded research group dedicated to studying anomalous astronomical objects without the constraints of government classification protocols. His team includes former NASA researchers, international collaborators, and private industry scientists who are free to investigate questions that official agencies seem determined to avoid. The shadow astronomy approach has already yielded significant findings that complement and extend the official research. Using privately owned telescopes and commercial satellite data, Dr. Chen's group has documented additional structural anomalies in 3I Atlas that haven't appeared in any official publications. Their analysis reveals faint geometric patterns in the object's nucleus that suggest internal organization rather than the chaotic structure typical of natural comets. The patterns are subtle, visible only through advanced image processing techniques, but they display mathematical relationships that are difficult to explain through natural formation processes. More provocatively, the shadow astronomy group claims to have detected periodic variations in the object's electromagnetic emissions that follow patterns resembling communication protocols used in advanced satellite systems. While these findings remain controversial and haven't been independently verified, they add to the growing body of evidence suggesting 3I Atlas operates according to principles we don't fully understand. The emergence of parallel research communities reflects deeper tensions within the scientific establishment about how to handle discoveries that don't fit conventional categories. Traditional researchers value peer review, institutional oversight, and careful validation of findings before public release. But these same processes can become obstacles when the phenomena being studied challenge fundamental assumptions about what's possible. Shadow astronomy represents an attempt to bypass these institutional constraints, allowing researchers to pursue questions and publish findings without waiting for official approval. While this approach lacks some of the safeguards of traditional science, it also enables investigation of possibilities that might otherwise be suppressed or ignored. As December approaches and 3I Atlas continues its journey toward closest approach with Earth, both official and unofficial research communities are preparing for what could be the most significant astronomical observation campaign in human history. The object will reach its nearest point to our planet on December 19th, providing unprecedented opportunities for detailed study. Major observatories worldwide have cleared their schedules for the event. The Atacama Large Millimeter Array in Chile will conduct continuous observations throughout the approach period. The Hubble Space Telescope has been repositioned for optimal viewing. Even the James Webb Space Telescope, normally focused on distant galaxies, will dedicate significant observation time to studying our mysterious visitor. But perhaps most intriguingly, several military and intelligence satellites have been quietly repositioned to provide additional observation capabilities during the closest approach. The specific reasons for this military interest remain classified, but the involvement of defense agencies suggests that someone in government circles considers 3I Atlas worthy of the highest levels of attention and analysis. The December 19th event is being treated as a potential watershed moment in our understanding of what travels between the stars. If 3I Atlas is a natural object displaying extreme but previously unknown behaviour, the observations could revolutionise Comet's science and our understanding of interstellar environments. If it represents something else entirely, the implications could be even more profound. The systematic study of our first confirmed technological artifact from another civilization would mark the beginning of a new era in human understanding of our place in the universe. Either way, the data collected during those crucial days in December will likely determine whether 3I Atlas remains a fascinating astronomical anomaly or becomes recognized as one of the most significant discoveries in human history. The synchronized jet systems continue their mysterious dance across millions of kilometers of space. The anti-tail maintains its impossible organization despite the chaotic environment of the solar wind. The wave patterns propagate with mathematical precision along structures that shouldn't exist according to our current understanding of natural processes. Whatever 3I Atlas truly represents, it's forcing us to expand our conception of what's possible in the universe. The question is no longer whether we're witnessing something extraordinary, but whether that extraordinary phenomenon represents the extreme edge of natural physics or something that transcends our current categories entirely. As we count down to the closest approach, one thing becomes increasingly clear. The universe is far stranger and more complex than we imagined, and 3I Atlas may be showing us just how much we still have to learn about the cosmic environment we call home. The answers we seek lie just weeks away, hidden in the data streams that will pour in from telescopes around the world and beyond. Whether those answers confirm our understanding of natural processes or challenge our most fundamental assumptions about reality itself, we're about to witness science at its most exciting and transformative level. The story of 3I Atlas is approaching its climax, and the revelations awaiting us may reshape humanity's understanding of our place in the vast mysterious universe that surrounds us. But there's another development that's been quietly building momentum behind the scenes, one that could provide the definitive answers we've been searching for. While the scientific community remains divided between official channels and shadow astronomy networks, a breakthrough has emerged from an unexpected source that threatens to resolve the mystery of 3I Atlas once and for all. Dr. Elizabeth Harper at the Keck Observatory in Hawaii has been conducting what she calls archaeological astronomy, systematically reprocessing archival data from previous observations using the advanced enhancement techniques that reveal the anti-tail structure. Her team has been working around the clock, applying modern image processing algorithms to older datasets that were originally dismissed as containing insufficient detail for meaningful analysis. What they've uncovered in the archived observations has sent ripples of excitement through both the official and unofficial research communities. Hidden within data collected during 3I Atlas's inbound journey, months before the dramatic perihelion display, are faint signatures of the same organized structures we're seeing today. The synchronized jet systems, the anti-tail formation, even the wave propagation patterns were there all along, operating at levels barely above instrumental noise. This discovery fundamentally changes our understanding of 3I Atlas's behavior timeline. Rather than the sudden activation everyone assumed occurred at perihelion, the object has been displaying organized activity throughout its entire observed passage through our solar system. The solar encounter didn't trigger these phenomena, it simply amplified them to levels where our instruments could finally detect them clearly. Dr. Harper's archaeological analysis reveals something even more profound. The intensity patterns in the archival data show gradual, systematic increases over time, following mathematical curves that suggest deliberate ramping rather than random fluctuations. It's as if 3I Atlas has been slowly increasing its activity levels according to some predetermined schedule, rather than responding chaotically to environmental changes. When plotted against the object's distance from the Sun, these intensity variations don't correlate with solar heating as traditional comet theory would predict. Instead, they follow orbital position markers, suggesting the object is responding to its location within our solar system rather than to thermal energy inputs. This positional awareness implies navigation capabilities that go far beyond anything observed in natural comets. The implications of Dr. Harper's findings are staggering for both camps in the 3I Atlas debate. For researchers advocating natural explanations, the data suggests we're dealing with physical processes operating according to principles we haven't recognized before. For those considering alternative possibilities, the organized position-dependent behavior strengthens arguments for technological interpretation. Meanwhile, the classification controversy has taken yet another unexpected turn. Sources within the intelligence community have begun leaking fragments of information, suggesting that the delayed Mars Reconnaissance Orbiter images contain evidence of geometric structures on or around 3I Atlas that don't match any known natural formation processes. While the specific details remain classified, the leaked descriptions include references to bilateral symmetry and modular components that sound more like engineering specifications than geological features. The mysteries surrounding 3I Atlas continue to deepen with each passing observation, challenging everything we thought we understood about objects from beyond our solar system. From the massive jet structures extending millions of kilometers into space to the impossible anti-tail-defying basic physics, we're witnessing phenomena that demand answers science may not yet be ready to provide. Whether 3I Atlas represents an extreme natural comet pushing the boundaries of known physics or something that transcends our current understanding entirely, one thing remains certain. The universe is far stranger and more complex than we ever imagined, and this remarkable visitor is showing us just how much we still have to learn about what travels between the stars.